again, Kostas is going to go into some detail on the Socrates fully coupled ocean run deck, and he's going to also compare that to a Q-Flux run deck. I don't think we have explicitly mentioned it, but there are two radiation schemes in the model. I don't know why. We should have mentioned it early on. We've kind of talked about them, but not directly. There is a default radiation scheme, which we call GISS radiation, which the Earth parent model uses. It's highly tuned for modern day Earth, atmospheric constituents, solar spectrum, etc., which has limited usefulness for us because we want to do other types of stars. So we have adopted several years ago another radiation scheme called the Socrates radiation scheme, which is described in the model description paper from the UK Met Office model, and that is plugged into our model. So in the planet branch and planet run decks, we use the Socrates scheme. That big S in the run deck template name means Socrates. That. And the O in this run deck name, P1SOM40, again means the fully coupled dynamic ocean. Kostas will go through a bit of that, and then we will compare it to the P4SQM40, the Q being a Q-flux ocean. For those of you that don't know the difference between a fully coupled ocean and a Q-flux ocean, I don't think I have time to talk about that at this exact moment, but I could go into some detail if we have time at the end of the morning session and explain exactly what a Q-flux ocean is and roughly what our fully coupled ocean looks like. I should just mention that in the exoplanet community, generally, when people have run GCMs in the past, almost all of them have used Q-flux oceans. These are shallow, 50, 100-meter deep oceans. They run them because they're computationally fast. They come into equilibrium very quickly, unlike a fully coupled ocean, which can be 5,000 meters deep. It uses more computational resources, and it takes longer for the ocean to come into equilibrium with the atmosphere if you have changed the forcing on that atmosphere. So we don't run Q-flux oceans that much because we have the computational resources to run fully coupled oceans, although we have run them for comparison purposes and to show people the differences that a Q-flux ocean versus a fully coupled ocean can give you.
Just to make one small comment that I think is important. So the Earth community historically has used Q-flux oceans a lot, although they've gotten away from that now. But Q-flux means prescribed ocean heat transport. The exoplanet community takes Q-flux ocean model and sets the Q-flux equal to 0, so there is no ocean heat transport.
There's no ocean heat transport between grid cells. There is transport between the individual ocean grid cell and the atmosphere, but there's no horizontal heat transport between the ocean grid cells.
Or vertical.
Well, there is no vertical dimension.
Well, in the ocean model there is.
Yeah, but in the Q-flux. In the Q-flux, there's only one layer.
Right.
That's right.
Right. Therefore, by definition, there's
yes, exactly. Yeah. So, and we will be providing that in Planet 2.0.
The same.
It's zero Q-flux ocean is the choice we made for the next generation of for our next review.
So when you say vertical there, are you talking about heat transfer within the ocean itself or between the ocean and the atmosphere?
So both of them do transport between the ocean and the atmosphere.
Okay.
Both models do. But the fully coupled ocean does transport vertically within the ocean. A Q-flux ocean only has one layer. So there's no vertical transport within it because it's just one layer.
But there is always transport between that one layer and the atmosphere.
Yes.
Okay.
Okay.
Okay. So we will be.
I'm going to stop sharing.
We will be discussing first this P1SOM40, which hopefully everybody was able to compile and run. Let's see. Get that?
Work.
Let's make that at a reasonable size. How does that look? In the back, you can see that easily.
Hopefully, I can turn the lights down. Is that what you're saying?
So,
is that better or worse?
Mike, the answer to your earlier question was that it was better.
The mic's on or off? Off. Okay.
Okay, so this is, you can either see the screen or you can see the run deck that you have already used before you came here. It is the P1 SOM40. And so it will always go all the way down. Out. Result. Oh, that wasn't good. Look at this. Yeah. There you go. I don't know why you're saying still saying. Okay, well, because you can hide it. When you have an Alt button, this is freaking Mac. So okay, I will not be discussing the last two lines of the run deck so that you will be seeing it better. Okay, so so this is at the very top of the run deck. The very first line says the name of the run deck itself, and then some comments, and then more comments follow until you reach this line that says preprocessor options.
Again, these are the comments that are mostly outdated.
So yeah, don't trust those comments too much.
You can see 2009 that's at the top.
And then after preprocessor options, it's the interesting part of the run deck that starts. So this part, preprocessor options to end preprocessor options, is the part that Igor mentioned we forgot to say in the previous slide. Okay, so you define certain things, and these are CPP directives. So you will see inside the model lines like, if def use end, then do something. And these are pieces of code that will be totally included or excluded depending on those commands here. So if you have, for example, in your Fortran code syntax errors and you don't include those pieces, then they don't matter. It's like they don't exist. And if you want to add some new feature that you want to test or you don't want to commit, you can protect it in your model with those if-defs in the source directory, in the Fortran files. You protect it with the if-defs, and then you define them here for you, and then nobody else has them really, because they don't define it themselves. It's a way to enable or disable components, or enable or disable testing, or you can use it any way you like. We have maybe 200 or 300 of those in the model. Of course, not documented, most of them. And but the key ones are the ones that you will be seeing in the template run decks. Then the object modules start, which is the part that I was telling you that contains the actual Fortran files that live in the module directory. So every line here, before the exclamation mark, of course, shows them. That's my mouse. Forget it. So every line before the exclamation mark defines file names with a Fortran extension. And you don't have to define the Fortran extension as already said. So you can see here which files are being compiled, and I'm going further down, and there are many more files, and there are some comments next to them that they say what these files are doing. And if you go, for example, in the clouds line, there are 3 files listed here with spaces, or you can separate them by new lines. It doesn't matter. The point is, you list all the Fortran files you want to be used in the compilation in here. And that goes all the way down until this line that says components. And these components are starting, feedback. So these components are the subdirectories that I was telling you that they live in the model directory. So if you go in the module directory and do an ls, you will see that there is a subdirectory called dd2d, another one called Socrates, another one called end. And then some of those have options. For example, the options for end are the ones listed here. The options for the GIS LSM are the ones listed here. You don't have to worry about the component options, and most likely you don't have to worry about the components themselves. But the important thing is that you need to remember that there are also Fortran files in those subdirectories. And if you are searching for something, there are some chances that what you are searching for is in those subdirectories, and most likely in this very first one, the shared. I don't think you will ever see anything that lives in the other places except the shared one. And then a very big part of the rundeck is starting that goes here from data input files. So again, everything that starts with an exclamation mark is a comment. You ignore it. So these two files are just nothing. And then you define lines like these: AIC equals something, GIC equals something, etc. Let's take the first one, AIC. This stands for Atmosphere Initial Conditions, and it provides an etcdf file. So as I was saying earlier, you take the netcdf, in the Fortran code, there is a line that says open file AIC. And then there is a soft link that is created by the compilation process that links the AIC file to the actual file you are pointing here, which this file does not have a full path. It does not start with a slash. So the model will go and search for it inside the prod input files directory that you have defined, and you have downloaded all the input files.
Your model ERC.
Yeah, that is defined in your model ERC. I think GCM search path is called. Yeah. If you want to create a new file here that you share with everybody, and because it is testing, because it is you don't trust it yet, for whatever reason, then you can put it anywhere in your directory, and then you need to start it with a slash. So if you say here slash, so if I have it in my home directory, I can put it like this, okay? So it starts with a slash, it's a full path, and I have to define it exactly. And this part with the data input files is very long, contains a lot of stuff, and we will go through them as we go through. We will discuss some of them, we will not discuss some others, and that part ends down here. So this is the last line for the input files. So this file has no extension, for example, if it looks weird to you. And then the label and name list part starts, which essentially says, this is the rundeck name, and here are some comments. And the comment is wrong, as I promised you. And then the parameters section starts. And this is the part that I was telling you, you can change actually variable names. You have, for example, this line that says, let me find a line that is not very popular, variable underscore LK, okay? So I hate that I don't see my mouse. So this line, variable LK, okay, this says whether to the model, whether the lakes will be variable or essentially dynamically calculated, or they will be fixed. If you go to the model directory and search for this variable, you see at the very bottom that says lakes F500 call sync param. This is a line that says, go in the rundeck, check if someone has defined this variable in the rundeck, and if yes, use the value from the rundeck. Otherwise, use whatever default value I am telling you that you have. And this default value is in line 60, lakes.f line 60 in the middle of the screen, variable lakes equals 0. So if I go in the rundeck and say variable lakes equals 1, because of the sync param line, this default will be overwritten. And you can add anywhere you want things like this. Well, not anywhere, it has to be a variable, a Fortran variable, not a Fortran parameter, because the parameter cannot change a number, a value. So this is how it works in general for so there will be plenty of those parameters here. We will go through some of them, not all of them. I mean, I don't even understand what some of them mean. For example, those drag here, things here, black box. But there will be other things. This is an important part, spectral file, that you define which spectral files you will be using, and the solar spec, which is your star. And these are important things. You need to have them in your Socrates path, if you're using Socrates, of course. and you can generate them, or you ask Eric politely. And, and then we have some key parameters here that are related with the balancing. I don't know if we will go through that, but these are some important factors that you need to know. Things that end with an uppercase X are multiplying factors for atmospheric constituents in the radiation. So CO2x equals 1 says that whatever the default CO2 concentration is, multiplied by 1. So essentially keep it the same. And the next one says whatever the default for ozone is, multiplied by 0, so disable ozone. And that is in radiation. We're not going to discuss interactive atmospheric composition with tracers and aerosols and stuff here, but these factors are only applied in radiation. And then also disable here the stratospheric water. And then there are other parameters that we don't have to worry about.
Let me just say, it's not disabling stratospheric water.
It's
disabling a model quickie parameterization to, or in lieu of a parameterization, it is disabling something that mimics the chemical production of H2O, or the right the.
Yes. It's not the setting water to 0. Yeah.
In the stratosphere.
Yeah.
The dynamics and thermodynamics of a model with the water ocean and so on and so forth can put water into the stratosphere, which is very important for exoplanets and habitability and stuff like that. This is something different from that has to do with the fact that this is not coupled to a chemistry model in which water can be produced thermodynamically.
And okay, then we have this line here, which is telling to the model which is the default year that we are going to simulate. Now, for exoplanets, this sounds irrelevant because we don't really have years, right? But this is relevant for two main reasons. One is that there is a file called GHG. Let me show it to you. This one that contains the data from of the greenhouse gas concentrations that you will be using. So if you open this file, which is ghg.mark 2009. So you see that there is a file that contains a lot of years, okay? And at the top there is the header that says with every column which greenhouse gas there is and the units. And then by saying master year equals 1850, essentially you say go in this file that I defined in the greenhouse gas as the greenhouse gas file and pick those values and use those in radiation. So you don't have to have a full list because this is just Earth inheritance. You can have a single line that says this line, use this line, pick a random year, doesn't matter. I think it has to be 4-digit. And then the model will be using those. If you use a different one, the model will use the closest. So if I would have said in master year down here, 1750, it would say, okay, there is no 1750. The nearest one is 1850, I'll pick that. And I think the same happens for in-betweens and no interpolation, but you will not be doing those things either way, so don't worry about it.
And this not only for radiation, but for everything. It happens that mostly radiation cares about it, but for CO2, it's not only radiation, but also vegetation. So if for some reason you decide to run your model with vegetation, if you think that your planet is habitable, then you should be careful about CO2 because vegetation that you are using is Earth vegetation, so you cannot change atmospheric composition too much. Well, at least in terms of CO2, there should be some reasonable amounts of CO2. Otherwise, the model just usually it would crash if you have too little CO2, or I don't know, probably would not crash if you have too much, but might produce something completely meaningless. So we should be careful about that.
So there is one more use that master year can do. It's setting that to 0. So if you set that to 0, it is the way to tell the model to run in transient mode. So think of present day of an Earth simulation. If you want to run from 1850 to 2000 and change emissions and the CO2 and everything as the model progresses, the way to do it is you set master year to 0, and then I'll show you in a minute how to actually define the transient mode. Otherwise, it doesn't matter which year the model thinks it simulates. It is actually simulating the one that master year says. And that will make sense in a minute. So there are more parameters here, and the end parameters line is where things stop. And then is the last part, the input Z. So this thing has 3 lines. The first 2 define the start and end time of the model, and the third one says how long the setup hour will be. Now, you have run the setup hour. The way the model works is that
The cold start.
The cold start, yeah. So the way the model works is that it has some initial conditions file. I showed you one as an example at the beginning, the AIC file. And there is also the GIC, ground initial conditions, and the OIC, ocean initial conditions. So when you start the model with iStart equals 2, this is what we call a cold start, which means go into those 3 files, use them, initialize the model with that, and start running. Now, that's a weird and exceptional way to start, because the model will, in its lifetime, as it runs with wall time, it will stop and start probably, and then it will usually not start from some random initial conditions. It will start from its current state. So to make that more natural for the model to start, what we do is that we start the model with the cold start, and we say, okay, go for an hour, which means 2 time steps, save a restart file, and stop. And then anything beyond that is a continuation from a restart file, which is the natural way of the model to work. So what we do here is we go to the first line, we say, okay, start from 1949. Remember, this is a random number, totally random, because master year is 1850. So no matter which year I will put here, the model will simulate the actual 1850 year. Then start from this random 1949, month 12, date 1, and hour 0. So the turn of the month from November to December. In the cold start, run for 1 hour, because you see at the very end, hour E equals 1. And then save the restart file. And then for every restart that it will happen later on, run up to the year E, which is the end of day 1, essentially the beginning of day 2. So the model will run for a full day, as it stands like now. And yeah,
So if you want to run for a month, what do you change?
Month E and year.
In this case, you have to change month and year.
And year and date.
And date.
Otherwise, you run for 32 days. And so a very typical mistake that people do here is that they play with those things, and you know what? The model is not starting. Or the model starts with the setup hour, and the setup hour lasts forever. It's like an hour, 2 hours. That's because you changed year I and year E, but you forgot to change the third line. It's a very, very typical mistake. Don't feel bad doing it. I still do it. And then I mentioned the transient mode. If you want to run, for example, a full historical period, 1850 to 2000, it's not happening for planetary cases, but for completion, if I set master year to 0, then those numbers, year I and year E, do matter. If I will run like this with master year equals 0, then the model will simulate the actual 1949 December.
If I want to run for 1 month, can we just go through what? If I want to run for 1 month, I'm going to set what?
So you set this to 50.
Okay.
You set this to 1. I tried, but I'm looking at that screen that has a lag. So I should look at my screen. And you change that to 1.
Bottom line.
The bottom line, you don't touch it because it is 1 hour ahead of year I. So if you change year I, then you change the last line as well. Otherwise, you don't have to.
And is there any significance in changing that bottom line to like a longer time span, or is 1 hour always like
We
the?
do that for debugging purposes. Yeah.
You can set it for anything. I mean, if you really want to, you can do your entire run.
Yeah.
Like if your computer doesn't stop, you can run for like several months of computer time just with this line. But there is no insurance. I mean, if it stops, well, I guess it will still be like.
Well, you will still be getting the full files. Yeah. But
anyway,
it's non-standard. I mean, you can do it as you like. So when you use a supercomputer, there are limitations on how much wall time you can use per simulation. So that's why we need to have a restart files. And so in our case, you can run, depending on in which queue you go, we can run it on for 12 or 24 hours. And then we must stop the model. Otherwise, it will just crash. The computer will kill it. So if you have no limitations, who cares about running a setup hour? You can do everything as a fake setup hour. But it can be weird if you have to stop the model.
It's just more convenient. It was set like that because usually when you debug the model, the first time step, it's important because if the model is doing something completely stupid, you can see it immediately. And usually after the first time step, we print partial diagnostics. Probably we'll discuss it later, which you can look at. So if you do something that like significantly change the model, you may want just to look at the output right after the first hour to see if it's meaningful and not waste your computer time. So that's why we always stop after the first hour.
The hour E equals 1 means that you're gonna write the output after every hour of what
1
the
hour.
conditions
The
are.
first
After just
The
only
first
the
time.
first
The
time.
cold
No,
start
just the first time.
Just 1 hour.
I see.
And then it will be just a regular 1 monthly.
Okay.
Because you run the model 2 different ways. In the instructions we showed you, there's a cold start. And that cold start uses that last line. So it runs 1 hour. And it generates a netcdf file called partial
Okay.
and the run deck name. So you can look, like Igor's saying, at that file to make sure everything's looking okay. You can also look at an output file for the model run itself. It ends in .prt. But then when you want to run the model, after you've checked it, everything's okay, then you run the model without the cold start on the command line, and it runs for year E, however long it should run from that. And
So
there was a question about what iStart and
yes,
iRand
I was about to answer that. So I see that the iStart is some magic flag we have that is allows the model to start from in different ways. So the 2 means cold restart from the initial conditions files that you provide. 8 and 9 are different ways to start from a restart file that the model saves at the end of the month or every time you request it to save. And there are some other internal flags that are 2-digit, like 11, 14. You don't have to worry about that. Practically, you will only be using 2 or probably 8.
We'll talk more about that.
Yeah.
Yeah, the difference between 8 and 9, that 9 is usually basically just to restart exactly the same run, like when you want to continue your run from restart file. For example, you were running, doing your run for a very long time, and then it crashed, and you realized that you have to change something very simple to continue. So you change that, and you want to continue that run exactly as it was. So you use iStart equal to 9. If you want to just start a new run, but you want, instead of initial conditions that we use, like with iStart equal 2, you want to use initial conditions which you created by doing some other run. So you already have kind of equilibrium condition for something. Then you use iStart equal to 8. So that's basically.
Is this kind of stuff in the user guide or documented somewhere?
Scattered around. These are basic commands. These are basic things that have been in the model for years, but I wouldn't trust it. No, they are documented in the video we're recording right now.
We'll talk in depth a little bit more about it.
Yeah.
And just briefly want to say in general about the structure of run deck. It's of course in home bred, basically a kind of like weird language, but as any language, follow some logic. For example, if you repeat this assignment several times in the code, then the latest one will take an effect. So if you overwrite something that you put previously in the run deck with something different, then the last statement that you put in will take an effect.
Like if you have k copy equal to 1 now, and you add a line after it that says k copy equals 2, it will use k copy equals 2.
Yes, so that also goes with input files, but you better don't do this because it may have some weird consequences. Yeah. And about this input, so last blog, I just want to mention that we treat it in a very trivial way. So for cold restart, we basically execute everything. So we just the third line overrides the second line basically with those ending times. But if you don't use this option called restart, then the last line is just eliminated from the run deck, basically how it's executed. So our scripts don't see it, and actually indication that is like special line. It's that it starts from the words I start equal to something. So those lines will be removed if you don't use called restart option.
So for new runs, do you do the cold start?
Yes.
Yes.
Unless someone else gives you a restart file to start from. Yeah.
We'll talk about that more later.
Pretty much, yes, nearly everything, always.
Then there is another question about the irand I that you can see here. So this has to do with the random number generator in the model. And if you keep it the same value all the time in all your runs, then you can exactly repeat them again and again and again, unless you change computer or compiler, of course. If you want to run with a different initialization of your random number generator, you change this number to something else. I guess any number you can go there, right?
Probably I never use it,
but essentially it has to do with how random the random number generator is in the model. I mean, what's the seed for the random number generator?
It may be useful for running ensemble of, of runs if you want to then slightly. Another question is, when you say stop the model, does that mean kill it, or is there a soft stop option? So we will talk about that later. The short answer is yes, soft option, soft stop. We call it graceful. Okay, I think we can go back to the slides.
Well, we were going to compare. Do you want to do that?
I'm sorry.
That's okay.
Okay, let's do that.
We're going to compare two run decks now, a fully coupled ocean run deck, which we've been looking at, and a QFlux run deck, just to show you how the input files look a little bit different between these run decks, rather.
Okay, so we will be comparing the run deck that we have, which is P1 SOM40 with P4 SQM40. So I don't have that here, so make run deck on SRC.
Please.
P4 SQM40. Unfortunately, I can't, but it will come up when I will present there. Sorry about that. Run close P4 40. Okay, and then div. So on the left is the QFlux run deck, and on the right there is the minimize it.
Yes.
So and on the right is the coupled ocean run deck that we were just looking at. And of course you see that the comments are different. Then there is define check ocean, which defines that in the run deck that use a dynamic ocean, otherwise don't. Then there is a file called ORES that defines the ocean resolution. It says it is a 4x5, 5x4, okay, ocean with 13 levels. then for some reason the advection schema in the atmosphere is different, it doesn't matter. Then there is a block of code that is different, so it provides more source files that are related with the dynamic ocean calculations. Actually, it is all the calculations that needed for the dynamic ocean to work. And then that's it. In the components, there are no differences. In the component options, there are no differences. And then in the data input files, there are some differences here. So there is an extra OIC on the right side window. That is the ocean initial conditions. You don't need that on the QFlux on the left. So there is no initial conditions for the ocean because it is just some fake ocean. That fake ocean needs to have some CI and fraction that is defined with the ZSI FAC. And then there is the ocean heat transport file that is defined. And then some relate, the OHT.
So in this case, this is an Earth ocean heat transport input file. So it's not like we were discussing before where there's no transport between horizontal grid cells in the ocean. In this case, it's prescribed based on a fully coupled ocean run. So the Earthlings like to run these QFlux oceans where it's prescribed the heat transport, and it's seasonal. So because it depends on what season you're on Earth, what the heat transport is between grid cells. So in a QFlux ocean where you don't have heat transport, you will change this OHT file, for example. So right now you're looking at a default Earth one that has a 65 meter deep single layer MXT, mixed ocean layer depth for that QFlux. You can see it even tells you what years it's valid for, 1956 to 1960.
Then look at the topo equals line that says which is the topography of the planet itself, which exists also on the right side. It's a couple lines up. And then the right side, though, has also a topo underscore OC, which is the bathymetry, essentially, topography of the ocean. And then there are other input files that I'm not going to bother. I mean, there is a comment that is different there. And then the Rundeck name down here is different in the label. And then in the parameters, there are some different parameters that are needed for the QFlux on the left and the dynamic ocean on the right. The tuning parameters are different. I don't think we discuss about those, and some comments, and that's it. The Rundeck, other than that, is identical. So there are some changes. They are not that numerous, and they are pretty straightforward. And that's about it. Then, do we need that?
No, maybe not.
Okay.
Do we want to compare them?
They are vastly different.
Okay.
So let's go back to the slides then. Can you share?
Oh, yeah, sure.
You guys recording and YouTubing this whole thing?
We are.
Good.
We are.
Okay, so we've done the top two. We are skipping the PS Mars because it is really, really different. I mean, essentially, there is no point in comparing the two. The Mars part has nothing about vegetation, nothing about oceans. It only has like 10 input files, and that's it, and very few parameters. You can go on this link and see exactly all those variables that are included in the model. Because every time you compile it, there is also an online documentation that you can access. It is very, very expensive. And so you can take a look to see what's there, but you don't have you don't have to do it now. Okay, go to the next slide. Oops, you went too far. Here. So we discussed this, which is the input Z and what everything means. And the master year, yes. And then here, we also discussed that, right?
We did.
Yeah, so let's remember what happens from the documentation. We did the make Rundeck. I just did it also today. And then the get input data script in the third line from bottom takes all the input files and puts them in a place that the model knows how to take with when you define it without the starting slash. Yeah.
I'm sorry, in the rundeck start.times, did you guys mention what the K diag was?
We didn't mention what most things in the rundeck.
Most of the rundeck things we haven't mentioned, yeah.
So just about master year before we move on. So if we set it to 0, what does it take for the initial conditions of the greenhouse gases? I'm not sure.
It takes, you define here, if you have year I 1897,
Yeah.
it will take that.
Oh,
And then after a year of simulation, it will move in year 1898 and it will take that.
As they're defined in,
Yeah.
what's the point of master year then if you already?
Because if you want to simulate 1 year as a climatology
for 100 years.
for 100 years, or if you are simulating another planet that the year is totally irrelevant, things don't change, then you set that to a fixed value,
Okay.
and it ignores those two and picks that one from the greenhouse gas file.
Okay. Okay.
It's a legacy of the Earth model. It's
Well,
something that we would probably not use.
It is basically defined if you want to run your model to get an equilibrium, or you already start from some kind of equilibrium and you want to perturb model to do something like this. Yeah, that's what we are doing with Earth. We usually assume that pre-industrial Earth was in equilibrium, and that's why 1850 that was used like this. We said that master year, we run it for a very long time, sometimes for thousands of years to get perfect equilibrium. But then we know that the Earth is not in equilibrium anymore, so we switch it to like real year, and then we use like a lot of stuff like greenhouse gases, aerosols, and everything that we derive the model. This is change every year, and that's the year we will be getting from the calendar.
Maybe we can look at the file quickly. Maybe I can bring it up.
The greenhouse gas.
Yeah, we can just show what
Yeah,
that
we
looks like.
showed it earlier.
But we didn't look at it in detail. Just let me try.
While you bring it up,
Yeah.
There is also another question I missed in the chat window. The QFlux ocean model has only one layer, so it cannot do anything related with the bottom of the ocean. It doesn't even care where the bottom of the ocean is. The dynamic ocean can simulate the ocean currents and transport in the ocean, but as the example in the question says, ocean floor sequestering of CO2 and the like, we don't do that. This is geologic timescales. We don't do those things.
Well, because ocean biologists, we do sequester CO2
In the water,
yes,
not on the
but
floor.
not on the floor.
Not on the floor. So yeah, this is the greenhouse gas file.
Yeah, and you can see that things are changing because we know that Earth's CO2 is going up since industrial times have started, and you can see that those values go year by year by year by year, up and up and up. And then you'll start seeing the CFCs come in as we start producing CFCs on the right, parts per billion. And then we go all the way down to 2009. You can see that looks very different from the first lines of the file. So now we're at 385 ppm CO2 instead of 285.
And if you go into our website and download the input files from the runs that Mike has done, for example, for his papers, and you'll get the GHG file, it will be a single line, 1850.
Yeah.
Okay.
And it will have the constituents that we used for that run.
Yeah, and the number is just nominal. It's just the number we use for the master year. It can be 2367. Doesn't matter. It's just a year.
Yeah. Okay.
Good. All right. Then we were going to look at, I guess we were going to try to, I guess they've run the model. What do you feel like? Should we have them run a test model? I guess they've already done it in theory.
Yeah.
So why don't we talk about tracers? Do you want to talk about that?
So yeah, very quickly, the thing about tracers.
Do you want me to draw it, or you want to?
Why don't I do that?
Probably because I'm not sharing it.
No, share that yourself, because then you take over after that. Okay, so a quick thing about interactive atmospheric composition. And I am not talking about the major gases in the atmosphere, so I'm not talking about the nitrogen or oxygen or any other major gases, but for tracer amounts. We have non-equilibrium chemistry in the model that is of course tailored for present-day Earth, and it can work for certain other conditions with lower oxygen, but not zero oxygen. And then it can. We have another under development. An update of this chemistry, actually a replacement of this chemistry with something more flexible. We call it KPP, which stands for kinetic preprocessor, which essentially is able to take any set of reactions and solve them by itself without having us to solve it. So we give literally reaction rates in a human readable format, and then the model figures out what to do. This is still work ongoing, and it's not available yet. For aerosols, we have 3 different schemes. The last one will be abandoned most likely, so we will stick with the 2 top ones. One is OMA, one moment aerosols. So the model simulates the aerosol mass only, and then you have to make external assumptions about the aerosol size of this mass, and that will not change with time. And the other is called matrix, which resolves both the mixing state and the size distribution of the aerosols. So it is able to simulate the aerosol growth, how it coagulates, condensation that happens, and of course all the optical properties that affect radiation are a function of size. These things are available in the model, and they will be used quite a bit in Planet 2.0.
Did the chemistry talk to the cloud parameterizations? Like if I change my nuclei for cloud droplets to grow, then the cloud model will also know about that?
In a very basic way. I think Tony can say something more about that.
So in next generation model, there will be explicit nucleation of cloud droplets by specific aerosol species for calculating aerosol and direct effects and the like. For Planet 1.0, that's not there yet.
And neither in Planet 2.0. It will be in Planet 3.0. Yeah.
You can do things that even in Planet 1.0, like specify a number concentration of aerosol, but you can't tell it, oh, this is sulfate. Water like sulfate to make a cloud droplet or something like that. You can't do that, right? But you specify a number concentration that can differ between land and ocean, between liquid water clouds and ice clouds. If you want to do, let's say, the type of thing that Tad Kovacic did in this recent paper, where he varied it, things like that. That's easy to do. Although actually our number concentrations, even in Planet 1.0, vary according to liquid water content, or I should say our particle radii vary according to liquid water content. The number concentration is specified, but particle radii droplets get bigger the larger the liquid water content.
Okay, so a few other things about the files that you can find. So we said that there is, when you start running the model, there is a directory saved, created somewhere where you have a lot of disk space, and then a soft link is created that points to that directory that stays in your DEX directory. So if you go in this output directory, you will see a lot of things, and some of them are, there is a file called I. It's uppercase I. And this file is a transcription of the run deck that you used in a stripped down version that contains no comments, no empty spaces, no nothing. It just writes the useful lines, everything in there. And that is the one that is actually being used as the model is running. So if during the model lifetime, you decide for whatever reason to change something in the model in real time, then you do not change the run deck. You change the I file, and you do some other magic.
Well, you stop the model first.
And that's coming a little bit down. So, so it is the I file that matters really as the model runs. Then there is a file called lock. And this file is there for safety, because as the model is running, you might do something, I don't know, you are tired or you're just thinking something else, and you try to run the exact same model in the exact same directory. This log file will protect you from overwriting what you're actually doing. And the caveat is that if your model for whatever reason crashes, this log file survives. Again, for safety, probably, or maybe because there is the model literally crashed and there was no time to do any cleanup. So when you fix what happened and you want to continue the run, so maybe you change something in the I file, it's very frequent that this is one of the scenarios, then you have to manually delete this log file which says essentially to the model, okay, I know I am going to rerun something in that pre-existing directory.
Usually run script will prompt you, will tell you that log file is present and show its location. So.
Yeah, you will get a very clear warning that, hey, there is a log file, maybe you won't delete it. Then during debugging, you might see that if the model crashed and you have no idea what's going on, or you are just developing something new and you want to see that everything goes fine. So we have this at compile time, when you do make setup and you say run equals your run name, you can append with compile with traps equals yes, and you may or may not want to add these extra S flags equals mine uppercase O 0. And that tells the model to run in a specific debug mode that tries to catch as many errors as possible. So division by 0, or usage of a parameter that has no value yet, a Fortran parameter or Fortran variable.
Or an input file that doesn't exist that you put there.
Yeah, or you try to put some index in an array that is beyond the bounds of that array. And it catches things like this, and it is really, really useful when you're doing model development. It's really important to make clean before, because otherwise you will not be compiling anything. It will find pre-compiled model and will not do it. And make clean after you figured out what happened and you fixed it, because there is a huge performance penalty when you do it. You don't want to run your production run with traps enabled. And then lastly, which is relevant with how the model stops, there is this tool that is called SSWE. It lives in the exec directory in the model root. And you simply, if you are in the dex directory, you just type this, exactly as you say it, /exec SSWE, and then the run ID as you have named your run. And that says to the model, which is already running, I want you to stop whenever you can. So the moment you type this command, it doesn't mean that the model instantaneously stops. If you check out your queue immediately, you will see that your model is still running. What it tells the model is when you have the time, when it's a good time for you, stop, which means that the model will finish the current time step, will save a restart file to disk, and then stop. And then anytime you want, you restart your file, your run with the standard command that you use to restart it.
Also, if you run your model just on your laptop without API, basically just in a serial mode, in theory, just normal Control-C is not supposed to interrupt it immediately, but rather that Control-C will be interrupted and the model will try to stop gracefully. Better don't do this, but at least something like that is programmed in. And that also should work. Sometimes it works, sometimes it doesn't work with queues on supercomputers. Because if everything is programmed correctly, then a supercomputer is supposed to send you a signal, terminal signal first, and then give you time to stop. So if that supercomputer gave you enough time to stop, then the model also is supposed to stop gracefully and write the checkpoint file before it terminates. Yeah, and if it doesn't stop gracefully, then you will get that log file in your run directory, so you will see that something didn't work.
So a standard, if you are using on a supercomputer that has this time limit I was telling you, you need to run SSW just before the maximum time has reached. So what we have is that we have this 12-hour limit, and we have a cron job that runs in the background for us. And then every time the model has less than an hour in the queue, it automatically stops the model and resubmits it. So it happens behind the scenes. Or if you are running it again on your laptop and you want to go and you want to turn it off, you just do the SSW, you turn the computer off, you turn it on back on later. It's a very useful tool you will be using most probably. I got a question on online privately so you will not see it in your chat window, on whether we will be discussing how to actually do the job submission on a computer. And we will not be doing that because it depends on your computer.
You've already done it.
So yeah, and well, yes, but on a supercomputer, you might want to go through the proper queuing system.
Yeah, and that's different on every computer.
Every computer is different, so we will not go through that. You have to go through that with your administrator. We can give you some ideas and tips on how it should be done in general, but essentially the way to do it is that when you were preparing to come here, you did make run deck and then make setup. That did the setup hour, and then you ran a command that said .exec, I don't even remember it. Yeah, .exec /run e whatever. That command needs to be submitted through your queuing system, and you have to figure out with your administrator how to submit that with a proper job in a supercomputer.
Well, in some sense, we made it, I made it, I think, really simple, but you still have to talk with your system admin to find out what is the command to submit a job. But basically, in your model ERC file, you can put just one cryptic line, which basically describes that command, and that command will be used when you use run e command. So, I don't know, maybe during the discussion I can show it like how it's done and discover. Okay, so, yeah, maybe this afternoon. Yeah. But anyway, it's not very difficult. It's just one line in model ERC that allows you to specify the way to start your queue, like at least with Slurm and PBS system.
These are supercomputer queuing systems. Again,
yeah.
Every center probably uses a different queuing system, or there's a few out there, but they're different. And the way you submit in these queue systems are different for each supercomputer.
Okay, and just a bit of history again, so that people are not puzzled what SSWE means. Well, E means at the end means E model version of the model, but SSW actually means sun switch, and that was a really physical switch on one of the extremely old computers where people could switch it, and that would set some bit and some register, and the model could check that, well, this bit is set, so the model should be stopped. So that's the name that propagated from, I don't know, like 40 years ago.
Okay, so I thought before we take our break, we could quickly take a look at this P1SOM40 file and just go through a few things about it that would probably be useful for you to know. I think we've said most. Well, we haven't discussed them in detail.
No,
really.
not in detail.
But the idea was that we would take a look at this file quickly. So to do that, basically, you all have to open up. That's why we asked you to compile this model. I have people's attention now. Open up this this run deck that we had you run the first hour of. So see if you can open up this run deck, the P1SOM40 run deck file. You have it on your desktop there. And we'll take a look at a few things. I mean, Kostas already looked at a few things when he compared it to the QFlux. He showed you some of the key differences, but we could just, I'd like to reiterate a few things so that you're familiar with these rundeck files. That's why we want you to take a look at them. So we can take a look at this very quickly and go through some of the things here that is good for you to know in general. So see if you can open up that file, the P1S OM40 version of your, I think we called it test or something like that.
Underscore test.
Underscore test, yeah. So as Kosta showed, there's some key differences. One was the K-ocean flag, which tells it to use a fully coupled ocean. The OIC file is, again, this ocean initial conditions file. So there are two or three key files here that are different. There's the ocean initial conditions file, there's the topo OC file, which is the ocean bathymetry or ocean topography file. So let's say you want to use a bathtub ocean. A bathtub ocean is an ocean which typically takes all the continental shelf regions around the continents and makes it, say, 400 meters, whatever number you want. And then everything else in the ocean can be a bathtub and just flat. You can make it 3,000 meters deep if you want, for example. So you can create a file like this. It's a netcdf input file. You can look at the format of the current topo OC file that you have there, and you can modify this quite easily as a netcdf file. But that's not enough for the model to be happy. You have to make this file consistent with the OIC file, the ocean initial conditions file, which has temperature and salinity in very strange units. So this is just one of those cautionary tales. Don't think you're going to just change one file and it's not going to affect something else, because the first thing you do is you'll change your bathymetry and then the model will crash and you'll be writing us emails, why doesn't this work? And the first thing we'll say is, did you change your ocean initial conditions file? No, I didn't. Think about that. So we can give you some tips on that if that's what you do down the road. We just want to give you some heads up about that stuff. The other thing you have to be aware of is this O-straits file. As said here, I think Kostas must have written this, is a strange file.
I don't understand this file.
Yeah, there's some areas on Earth in the low resolution files where you might have a strait that's basically pushing water between two grid cell boundaries that are touching each other, but they're at corners with respect to each other. Maybe I should turn on my video. Happen to that? Well, let's go back here. Sorry. Get my.
Oh, and so is that intended to be for something like a coarse resolution model near the Bering Strait?
Yes.
You don't want to isolate the Arctic Ocean from the Pacific Ocean. If you're doing, let's say, an Earth paleoclimate with two continents that are relatively close together, but you don't want to completely isolate the ocean in one place from the ocean in another place, because in the real world there's a narrow strait there that the model doesn't resolve. That basically.
Exactly. So it just tells the model, make sure you let some ocean through these two grid cells that otherwise look like there's land there.
So yeah, a key thing that we haven't said is that for the dynamic ocean model, there are no partial ocean grid cells. So it is either ocean or land, end of story. In the fixed sea surface temperature configuration, you can have partial fractions of land and ocean, but for the dynamic ocean, you cannot. So it is either a strait that has the width of a grid cell or no strait at all. And that's what we parameterize.
Yeah, we haven't said it, but and Kostas touched on it here, but we won't go into detail, but there are actually three kinds of oceans you can run with this model. There's a fixed sea surface temperature ocean. Again, that's from Earth data, and we tell the model for a given set of years, these are the physical sea surface temperatures that the model will have. We don't usually run those in exoplanet scenarios. In fact, we never have run them. So we won't go into any depth about that. Then there's, of course, the Q-flux oceans, which are run in the Earth community, again, with fixed ocean heat transport fluxes, but typically in the exoplanet community, it's run with zero ocean heat transport because we have no way to know what the transport should be. And the third ocean is the fully coupled ocean. So if you hear us talk about fixed sea surface temperature oceans, that's that ocean that we basically don't run in the exoplanet community, but is run in the Earth science community.
Oh, by fixed you mean prescribed.
Prescribed.
It's not fixed in time.
No, it's not fixed in time. No.
Yeah.
It evolves in time. Yes. We have a little thing here about line 5812 and OCDYN. I guess I should talk about this quickly. Let's say that you want to run an aquaplanet. So that's a planet that's all ocean and no land.
At the surface.
At the surface, yes.
Not a water world as exoplanet people.
Yeah. The dynamic ocean model, of course, is always trying to find ways to save computational resources. So the default